We've seen this ideal block diagram of a pipelined ADC before, showing how each stage processes the signal and passes a residue to the next. Now, we're going to look at this from a more practical, real-world perspective. The components we use to build these stages, the op-amps, the capacitors, the switches, and the comparators, are not perfect. Each one has non-idealities that can introduce errors into our conversion process. This page gives us a roadmap of these key sources of errors. Let's look at the list. We can group these errors by the components that cause them. First, in the sub-ADC of each stage, we use comparators. The first error listed is comparator offset. In an ideal world, a comparator triggers at exactly 0 volts or at a precise reference voltage. But in reality, due to mismatches in its internal transistors, it might trigger at a slightly different voltage. This offset can cause the sub-ADC to make a wrong digital decision, especially for input voltages that are very close to a threshold. Next, let's consider the capacitors, which are fundamental to the switched capacitor circuits in the ADC. We have capacitor mismatch. The gain of each stage and the accuracy of the DAC subtraction depend critically on the ratio of capacitors. We might design two capacitors to be identical, but due to tiny variations in the manufacturing process, they will never be perfectly matched. This mismatch leads to a gain error in the stage, meaning the residue voltage passed to the next stage will be incorrect. The operational amplifier, or op-amp, is the heart of the ADC, and it's also a major source of errors. We have op-amp gain. We often assume in our calculations that the op-amp has infinite gain. Of course, real op-amps have a finite gain. This means the charge transfer in the switched capacitor circuit won't be 100% complete, which again results in a gain error. We also see op-amp offset, which is similar to the comparator offset. It's a small DC voltage at the op-amp's input that gets amplified along with our signal. Then there's op-amp nonlinearity. An ideal op-amp's gain is constant, but a real op-amp's gain can change slightly depending on its output voltage. This introduces distortion. The switches in our circuit also cause problems. One is charge injection mismatch. When a switch turns off, the charge stored in its channel has to go somewhere, and some of it gets injected onto our signal path, creating a small voltage error. If this happens differently between matching switches, we get a mismatch. Finally, we have a very fundamental limitation, kT/C noise. This is a type of thermal noise. The random thermal motion of electrons in the resistance of the switches creates a random voltage fluctuation. When we sample our signal onto a capacitor, we inevitably sample this noise as well. This noise is unavoidable and sets a fundamental limit on the precision or signal-to-noise ratio of our ADC. As the name suggests, it's related to the capacitance C. Using larger capacitors can reduce this noise, but that comes at the cost of more power and larger chip area. This list covers the main challenges in designing a high-performance pipelined ADC. In the next few slides, we'll dive into each of these error sources in more detail to understand exactly how they affect the ADC's output and what design techniques we can use to mitigate them.